All right, I think it's time. Welcome back. So we're going to talk some more about DFAs today. This is our first and kind of simplest type of simple machine that we're going to be talking about. I hope you recall from last time, maybe I'll just refresh our memory. How about a DFA for, these are the two examples we did at the end last time. A DFA to accept any string starting with A. This would be something like, here's my starting state, and the first letter could either be an A or a B. We were talking, these examples were just about strings of A's and B's. And if the first letter is an A, then it should be accepted sort of permanently. No matter what happens after that, you should accept a string which begins with A. That's what the rule says. And if it begins with B, it should be rejected regardless of what happens after that. So that should look like this. All right, I hope you remember how to think about these things. This is where you start when you don't know what it starts with yet. If it starts with an A, then that should be accepted. If it starts with a B, then that should be rejected. And it doesn't matter what you see afterwards. All right, so that's accepting any string starting with A. And then we also talked about how about any string ending with A. That actually looks quite different. It doesn't matter what it starts with. It's just that if the last thing you saw was an A, then it should be accepted. And so the way that looks is, when I start off, I don't care about B's, but if I see an A, it should go to the accepting state. And then after that, if I see another B, it should go back over here. And there should be an A like that. So the way that this one works is, when you start, it should not be accepted because it doesn't end with an A. If you just start from nothing, that's not ending with an A. But if you ever see an A and then stop, then it should be accepted. But if you see an A and then a B, it should go back to the rejection state, and so on. All right, this is ending with the A. Maybe could I have you guys all try another example? This is just a little warm-up for today. Can we do a combination of these two? Actually, this example, you can kind of just combine the two diagrams, although you have to think it through a little bit. But how about accepting any string starting and ending with A? That's what I want. Starting and ending with A. All right. So the way that I would think about it is, first of all, you have to do something like this to check if it starts with A or not. But then it shouldn't be so simple up here. You don't want to automatically accept. If it does start with A, you don't want to automatically accept. You want to do something kind of like that. But think about it. I'll give you a few moments. I don't know if it's too early to just start right out with this kind of thing, but I'm ready for it. I'll give you 2 minutes. Talk to your friends if you like, if you got any. It's okay if you don't. I don't really. In here, I mean.
You got
I mean, you all. I like you all so far. I wouldn't call us friends. All right, your 2 minutes are up. I don't know if you came up with something. Like I said last time, it does take a while to kind of get used to thinking in this way. Anyway, you should have started with this as a basic setup. So this one definitely will reject if it begins with a B, right? It's just the question of what to do if it begins with an A. It should not automatically be accepted because it also needs to end with an A. But basically, I want to put this up here. This bit here tests if it ends with a A. Now, by the time you get up here, you know that it already began with an A. So we also need to verify that it ends with an A. So the way that I did this, actually, if you think a little bit about this, I did not just directly plug that right here. You can do that, although that's not technically not exactly right. I said, come on now, this. So what you see here is like that, but I kind of turned it around. Why did I put the accepting state here and then it rejects? That's because if all I see is just A, then actually that should be accepted. So the string of just A by itself, that one actually does start with A, but it also ends with A. So if you read just A, that should immediately be accepted. If you see further A's, that should still be accepted because the last thing you saw was an A. But if you see a B, that should go over here to the rejection state, and technically I need one of those, right? If I ever see B's and then stop, it should be rejected. But if I ever see A, that brings me back to the accepting state. And I hope you wrote something like that. I don't know, does anybody have any questions about that? Or there is some opportunity for like, well, I wrote something different, but maybe that's still right. And that's true. There's not like a unique answer to this. Yeah?
So the bottom state is it's 100% wrong once it gets there.
Yeah,
The top
right.
We're just saying there's a chance. It'll still be right.
There's still a chance. Yeah, right. If you go up here, it is possible to fail. Like if the string was AB, then you would go here and then here and it'd be rejected. Yeah.
Wait, so I'm a bit confused as to why we need like the additional like circle all the way to the right.
This one here?
Yeah.
Yeah. If we didn't have this, so I will just temporarily kill that. Now, you need an arrow from here with a B on it.
Yeah.
You could just, if you wanted to say, just go back to here. Is that what you're thinking?
Yeah.
Yeah, then the string, for instance, A, B, would be accepted. You would go A and then B, and it would be accepted.
Or what I originally did was I drew another arrow from like the successful piece
Yeah,
to
go
like,
down.
No, to the left circle.
Back here.
Yeah.
Mm-hmm.
And I don't think it was right, but I just was wondering.
This is a good idea. I think not quite right though.
Yeah.
Because
You would be back
I
to
could
the
do
end
A, B, B, A. ABBA, if you will. That should be accepted according to the rule here, but it would be rejected by this. So yeah, that's a good idea, but not quite right. There's always some question about, I did this using 4 states. Is it possible to do it with 3 states? I think it's not in this example, although it's not obvious, and it's not, even if I wanted to like prove that, it would not really be easy to prove. Any other questions? Great. Okay, I just had one more that we can all think about together. This is any string starting and ending with A. What about, instead of and there, or? How about any string starting or ending with A? Starting or ending. Well, I'm going to, let's just to kind of get us started. Again, it matters what the first letter is, right? It's not, the first letter can be B or A, and if it's an A, then the string should definitely be accepted automatically, right? If it begins with an A, then certainly it should be accepted. So I'm going to start with one of these guys again, just because the first letter is important. But this time, if it begins with A, then it's an automatic accepting. So that looks like this, right? If it begins with A, it should be automatically accepted. And then, what if it begins with B? Well, at this point down here, it should be accepted if it ends with A and rejected if it ends with B, right? And that actually is going to look kind of like this, only accepting the B ones rather than the no, actually it looks like this, but it shouldn't be accepting to begin with. I think something like this, right? If it begins with a B, then you have to have an A at the end in order for it to be accepted. Now I need more arrows here. If there's a B after that, then it should be rejected again. If there's more A's after the A, then it should still be accepted. And if there's more B's before the A, it should still be rejected. All right. So I think something like that is the way to go for starting or ending with A. All right. The unfortunate takeaway from these examples is, first of all, if you feel like I did that really fast, like I always say, this takes a while to get used to. I think you will get used to it when you try out the homework problems. Another quick takeaway about this is, we did these two examples, and then basically I've combined them together using or and. This is the and this is the or. But there is not a simple kind of way that you can just plug two machines together with the word and, right? You actually have to think it through in detail to make this work. We are going to talk eventually about how could you just kind of like combine two DFAs together to make another DFA that does something related to the first two. But as far as the and or goes, there is no very simple construction which will make it work easily. All right? That's just the way it is. Great. What I want to talk about today is try to get started on a major question that's sort of like going to be a theme for the next couple weeks, and that is what types of sets, or would you mind if I say languages? Remember, language just means a set of strings. What types of languages can be accepted by a DFA? Like, I don't know if this even crossed your mind, but I suppose in any one of these examples that I've just been talking about, your answer might have been, well, there's no way to do that using a DFA. Like, probably, a DFA is such a simple thing that I assume it can't do anything you can imagine, right? So that's always a possible answer. If I say, make me a DFA which does this or that, maybe the answer is there just isn't a DFA which does that. Although, these examples we've talked about so far, there were DFAs that do that. But this is a question that I want to talk about. What are what kinds of languages can be accepted by a DFA? And the answer is you shouldn't just by default think that any language at all can be accepted on a DFA. But, we already know, so examples that we've seen so far would be something like on the alphabet with just a single letter, we can do the language of all even strings, right? That was the first example that we did yesterday, or Wednesday, was the language of all even strings, all right? And if you recall, this is a fairly simple example. It was like this, right? Length 0 would be even length, and so starting off, it should be acceptable. But if you read a letter, it becomes odd. If you read another letter, it becomes even again, and so then it should be acceptable again. And if you read some more, it flips back and forth between even and odd every time. All right. So this is a machine which accepts all even length strings. I left the word length out. I should say. Of course, a string itself is not even or odd, but I'm talking about the length. All right. What about, here's just simple variations on that. How about lengths still just using the letter A? How about lengths which are divisible by 3? Even means divisible by 2, right? Actually, there's a not so difficult way to modify this example to make it so that it only accepts when the thing is length divisible by 3 rather than 2. Anybody feel like you can change this diagram a little bit? Yeah?
Can you just add a third circle so it kind of goes in?
Yeah. Add a third state so that it's kind of goes like in a triangle or something, like this. And I'm going to make this accepting. All right. This time, we start off as acceptable because the empty string is length 0, which is divisible by 3. That counts as divisible by 3. And then if you see another letter, it's not divisible by 3 anymore. But if you see 3 more letters, it is divisible by 3 again, right? So it takes 3 steps to get back to the acceptable state. All right, so this one accepts lengths divisible by 3. All right, how about, okay, I'm full of variations here. How about not divisible by 3? Lengths not divisible by 3. Actually, this one, again, there is a simple, cute trick that you can use. I should probably put my little A's on there. Anybody have a cute little idea where you can make a machine which is accepting anything which is not divisible by 3 and rejecting something which is divisible by 3? You kind of want to do this, but like the opposite somehow. How would I do that on a diagram? Yeah, what do you think? Sorry, you can arm wrestle about it. No.
Go for it. Take the diagram you had before, but change the accepting to rejecting.
Yeah, just use the same diagram, but flip-flop all of the accepting versus rejecting. So we want it to do the same stuff, only if it is divisible, then we reject, and if it's not divisible, we accept. So that would look like, this. So the same sort of circle of 3 things, but these ones are accepting and the first one is not. All right, that's not divisible by 3. Could I make one for strings which are not divisible by 2? Yeah, we could just take this first one and flip-flop the states, right? How about not divisible by 2 or 3? You can do that too. It's not so hard to combine those 2 things. I don't need to go into the details about this. So could I just say, like, generally speaking, divisibility? How about divisibility is generally easy to do, right? Like, how about strings which are divisible by 8? Well, you basically do this. This is the divisible by 3. Divisible by 8, you just make it a lot bigger, right? It has to go around the octagon rather than the triangle, all right? Divisibility is generally easy to handle. But how about this? A DFA which accepts when the length is prime, a prime number. How do you like that? This is much more complicated. That, a prime number means it is not divisible by 2 or 3 or 4 or 5 or whatever, except for its own length, right? That is a lot more complicated. If I give you a very large number and ask you to tell me if it's prime or not, even like for a human being, that's not an easy question to answer. Although you could answer it using a calculator, just try to divide by every number. But in principle, you might, depending on how big the number is that I give you, you might have to divide by many, many numbers, right? This turns out to be not possible. I'm going to sort of put this in parentheses. Not possible with a DFA. I'm putting this in parentheses just because I'm not prepared to explain exactly why, but the idea that it's complicated. The idea that I have in my head is to check when a number is prime, if you don't know how big that number is ahead of time, you are going to perhaps have to be dividing it out by many, many numbers. It's impossible to predict, if you don't know the number ahead of time, how many numbers you're going to have to test. And the DFA has to be finite. This is the big thing. The DFA has to have only finitely many circles in the diagram. That's what the F means. That puts the F in DFA, is finite. To be able to check any number for divisibility by any other number, you should feel like maybe that's not even possible to do with a finite diagram. And in fact, it is not possible to do with a finite diagram, although that statement is not really easy to see exactly why that's true. But this is an example of something which is not possible to do with a DFA. It is, there are such things. Here's another one, maybe a little more down to earth or a little more surprising. To me, if you're asking whether a number is prime or not, I already know that's kind of a hard mathematical question to answer. Even for computers, like testing whether a number is prime or not is a big deal in sort of mathematical computer science these days, and there are not really good algorithms to do that. Here's another one though, which seems much easier. How about on this alphabet, just A's and B's? I would like to accept any string where the number of A's equals the number of B's. I don't care what order they're in, but as long as just there's the same number of A's and B's in the string as a whole, all right? This is an example, actually, this one also is impossible to do on a DFA, although to me this seems much easier. Like if you are using an ordinary, like an actual programming language, it's not hard to write, say, a program in Python that does this, that just checks if the number of A's is equal to the number of B's. But actually this too is impossible on a DFA. All right, and the issue is like the DFA has to read the string one letter at a time, and as you go down the string, apparently if you want to accept or reject the string, as you read the string, you need to keep track. Are there more A's or are there more B's from each at each point? All right, so here's an attempt. This attempt is not going to work, but the way that I might try this out would be the starting state represents. Here I have the same number of A's and B's, right? Because that's where you start with before you've read anything, you have 0 of each. Now, if I see an A from that state, it means I have one extra A. So maybe if I see an A, I'll go to a state which represents one extra A, right? One more A's than B's. But if I see a B from there, I can go back to they're evened out, right? So my DFA is just keeping track of how many extras there are of either the A's or the B's. So from there, if I see a B, then that makes there's an extra B, right? Like this. And if I see an A from there, I go back to the beginning. And this is the accepting state, right? This is the one where there are the same numbers. The problem with this is if I'm in this state and I see another A, well, that means now there's 2 extra A's. So I would have to make a new state for that, 2 extra A, with a B that goes back like that, right? If I had 2 extra A's and I see a B, then that means actually there's only 1 extra A. But this, if you really want to make this work, you have to go like this forever, and similarly here. So this strategy is a good idea, but it actually requires infinitely many states, which is not allowed in a DFA. So this requires infinitely many states. So it's not a DFA. All right. Now maybe there's some other strategy which actually works. I'm telling you there isn't. But actually it's quite difficult to prove that something cannot be done on a DFA, because you have to somehow, like in theory, consider all possible DFAs and argue that none of them could possibly compute what you want to compute. And that's much more difficult than showing that something is accepted by a DFA. Then you just make one diagram that gets the job done. All right. So the question of what kinds of sets can be accepted on a DFA is an interesting question. This is sort of like a long-term question that we're going to answer, eventually. But it's not for today. I'm just trying to get us started thinking about this. All right. All the examples we've done so far have been, I tell you some language and you make me a DFA which accepts that language. But we can also go the other way around. How about I show you a DFA and you tell me what is the language that is accepted by that DFA. So here's an example like that. This is another kind of thing that you should expect to see on the homework. By the way, I think we've done enough so that we can have our first homework assignment will be due on Wednesday of next week. later today, you should check out the class website, and you will see the first assignment on there. I usually wait till after class on Friday just so that I know how far we got. How about this? This is a DFA. Can you tell me what is the set of strings? What is the language which is accepted by this DFA? What is the language of this DFA? All right. You can explain it in ordinary words, like all strings that start and end with A. That's not correct, but that would be like ordinary words. Or you could write it as a set in set theory notation, which is sometimes more convenient. If you don't know what's up, it might be a good idea to just try and sort of write down a bunch of strings and ask yourself, are they accepted or not? So let's, I'm just going to sort of make up a bunch of examples just to see if I can think properly about this. How about these? Let's just check for each one of these. Is it accepted or rejected? The way to do it is you just sort of, you always start here, and then you just kind of jump around in the diagram according to what the string says. So A by itself, I start here, I do A. It is accepted, right? So that is accepted. Yeah, I'll just put a little check next to it. What about B? What do you say? Is B accepted? Yes. I see the heads nodding. If you start with B, you start here, you do B, that is accepted. So B is accepted. How about AB? That would be here. I go A is still here, and then B goes over here. Still accepted. So this is accepted. BA. I think BA is rejected, right? If I start here, I go B, and then A. That is in the rejected state. So this is rejected. How about ABBB? What do you think? Show me the thumbs. Accepted? I see the thumbs up. Yeah, ABBB is accepted. ABBA, what do you say? That's rejected. BABA. That's BABA. Yeah, that's also rejected. Anybody see a pattern here? Can you explain in words, perhaps? What are the things which are accepted? Yeah.
When it starts with all the A's and then ends with all the B's, but it doesn't have like A or B. A after it.
Yeah, this sounds pretty good to me. If it has a bunch of A's, that would be just going like this forever, for a while. Not forever, but. And then a bunch of B's. So you can do a bunch of A's, and then a bunch of B's will do this. But if you see another A, that'll be rejected. All right. So what it means is you have to have all the A's at the beginning, followed by a bunch of B's, and that's it. You can't have more A's after that. So how would I write that out in words? I mean, in ordinary words, you can try to write something like this. Something like a bunch of A's followed by a bunch of B's. It's probably better if you don't use the phrase a bunch. But that's the idea, a bunch of A's followed by a bunch of B's. I think this one is most convenient to write using set theory notation. So this would be a string which has a whole lot of A's followed by a whole lot of B's. Actually, this is not so hard to write. I would write it this way, A to the N, B to the M, right? And nothing else. So this means a lot of A's followed by a lot of B's. Now, when I say a lot, it doesn't actually have to be a lot. It could be, actually these N's and the M's, can they be 0? Could it be no A's at all? The answer is yes. It could have no A's at all. That's still acceptable. And it could also have no B's at all. That's still acceptable. And it could, in fact, it could have no nothing at all, right? They could both be 0. It would be the empty string, which is still accepted because you start in the starting state. So I'm going to write it this way, A to the N, B to the M, such that N and M are any natural number. And remember, in this class, the natural numbers begin with 0. So 0 is included as part of that. All right. Great. That's the deal. Okay, this set here, Sorry, I noticed something is not written correctly on my paper and it temporarily confused me. That set here, this is called, there's a name for that, the language of the DFA. So I could write this DFA, you know, this is like how I would say it on the homework or on a test. I write this DFA and say, what is, well, I just said that. What is the language of this DFA? It's the language which is accepted by that DFA, all right? And there's a notation for that. So if the DFA is called, when we write, like, you know, sometimes we're going to write proofs about DFAs or whatever, it's sometimes helpful to have a name for the DFA. If it's called M for machine, then L of M is the language accepted by the DFA. You could write that in fancy set notation here. This says the set of all strings on the alphabet such that that string is accepted by the machine. All right, I hope you remember what this sigma star means. Sigma is the alphabet. Sigma star means all possible strings. So this just says it's the set of all strings from that particular alphabet such that X is accepted by the DFA. All right, and this is called, like I said, the language of the DFA. And there's, you know, because I was trying to ask this question, what kinds of languages can be the language of a DFA? Like the language of all prime number length strings is not the language of any DFA. Or that thing with the A's, number of A's equals the number of B's, that's not the language of any DFA at all either. There's a term for that. So this is an important definition. A language is called regular. Regular means that it is the language of some DFA. So a language is called regular if there exists a DFA M such that the language, sorry, I should have put this. Sorry about this. A language L, if I start with some language called L, then L is called a regular language if there is some DFA such that L is the language of that DFA. All right? So regular language means there is a DFA whose language is the language you're talking about. All right? I hope you're familiar with this little guy here. This is a backwards capital E, which means there exists. So a language is called regular if there is a DFA such that that language is the language of that DFA. All right. So for example, you know, X in A star such that length of X is even. This means all strings with using just the letter A. That's what this says over here. All strings using just the letter A such that the length of X is even. This is a regular language because I can make a DFA for it. This is a regular language since, if you wanted to write like a little proof, I suppose, since it's the language of this DFA that we have so often used, right? It's the language of that. That's the DFA which accepts strings of even length on just the letter A. So that is a regular language, all right? Or for example, X equals, sorry, that's not what I wanted to say. How about AXA such that X is in AB star? I don't know if you're used to reading these kinds of set notations. What does that mean in ordinary language? This is the set of all strings that look like AXA, where X is any string on A's and B's. This just means any string which begins with an A and ends with an A, right? It has an A, then whatever, then ends with an A. So that's what that means. Is that a regular language or not? Yes, it is. This is one of those other examples that we already did, right? all strings which begin and end with an A. We made a DFA for that. So this also is a regular language. Because we made a DFA for it. That's what regular language means. All right. But something like, this X on AB star, this means X is a string using A's and B's where the number of A's equals the number of B's. This is not a regular language. Because of what well, actually I didn't fully explain this, but I'm asking you to take my word for it at this point. This is not a regular language. You might say it is an irregular language, although we don't ever say that. I don't know why, but you just say it's not regular. This is not a regular language. This is because since no possible DFA can have this language, but that actually is very difficult to prove, and I didn't fully explain why that's true. No possible DFA has this language. I showed you an attempt which failed, but that doesn't mean it's impossible. But I'm telling you, it is actually impossible. No possible DFA has this language. Can I just say this is hard to prove? To prove that a language is regular is easy. All you got to do is show me what the DFA is. But to prove that it's not regular, you have to somehow convince me that no possible DFA can make that language. And that's much more difficult from an abstract point of view. We are eventually going to talk about how you can prove that kind of a thing, but it's not easy to do. All right. Excellent. We have 13 minutes remaining. I wanted to do a what I would consider to be a more interesting example of a DFA. So far, I hope that you're getting the impression that a DFA is kind of like a very stupid computer or like a very simple computer, that it can answer some kinds of questions, like does this string have even length? It is possible to answer that question on a DFA. But certain other kinds of questions, like does a string have prime number length, that's impossible to answer with a DFA. So a DFA you can imagine to be some kind of a very simple kind of computer, or an instrument for doing some very simple calculations. It turns out, though, that you can use DFAs to do what are actually fairly sophisticated mathematical computations. So I want to do an interesting sort of a math type DFA. That is a DFA which actually makes an interesting computation, which is something that for an ordinary person is not very easy to do, but actually there's a DFA that does it very nicely. So this has to do with, this is an interesting math DFA on the alphabet of 0, 1. I want to do like real math with these. I mean, everything we've been talking about is kind of real math, but I want to do some sort of traditional numerical calculations here. An interesting math DFA with the alphabet 0 and 1. And this has to do with binary representations of numbers. So I thought maybe could we just do a little review about binary numbers? This is something I hope that you're familiar with, but this is about binary numbers. Binary is just a different way of writing numbers. We, ordinary people and most human beings throughout history, use the decimal system, which is thinking about numbers in terms of groupings of 10. So in decimal, we write, this is like the normal way of writing numbers. I'll go up to 11 here, 8, 9. See, the deal with decimal is we only use 10 different symbols, counting 0. Once you get up to 9, there's no special symbol for the next number. You carry over to the next digit, and then I'll just write 11 for fun. So once you get to 9, that's the last individual number symbol, and to make the next number, you roll the 9 back to 0, and you carry a 1 into the next digit over. All right, everybody knows this. What is binary? Binary is the same idea, only you only ever use 2 symbols. So you start with 0 and then 1. But there is no symbol past 1, and so you immediately carry over to the next digit. So the number 2 looks like 10 in binary. The next number looks like 1, 1, because just like in decimal, when you're increasing a number, you increase its lowest, the lowest position, the rightmost digit. But if that rightmost digit can't be increased anymore, you carry over to the next digit. So the number 4 looks like 100, 5 looks like 101, 6 is 110, 7 is 111, 8 is like that, 9 is, sorry, I'm not lining these up very well. That's 10. That's 11. All right, these are the same numbers in binary. I hope you've seen this before. Maybe you've heard the absolutely hilarious math joke. There are 10 kinds of mathematicians, the ones who understand binary and the ones who don't. Huh? You get it? Because 10 is in binary is 2. Yeah. I'm all about the hilarious math jokes. Actually, I, in general, despise math jokes. But, all right, this is decimal and binary, okay? What we're going to do is, I don't think we're going to be able to do all of this in our remaining time for today. But what I would like is a DFA which reads a string on zeros and ones, right? Which is going to look like one of these things, right? So the DFA reads one of these binary numbers and accepts when the number is divisible by 3, all right? And rejects otherwise. That's what the DFA is supposed to do. So the ones which are divisible by 3 would be 0 is divisible by 3, but also 3, 6, 9, and I guess the next one there would be divisible by 3, right? Those are the ones which are divisible by 3. So I want to make a DFA which reads a string one digit at a time, or one bit at a time. That's the word. Here's a little fun trivia fact. The word bit comes from binary digit. So the individual digits of a binary number are not typically called digits. They're called bits. Apparently, there was some people at when these terms were invented. Some people were saying bidget for binary digit, which sounds funny to me. They settled on bit. Bit is probably better. All right, a DFA which reads a string of zeros and ones, and it accepts, it is able to tell you whether or not that binary number is divisible by 3. This is very interesting to me because this is something that an ordinary human being cannot do. Like if I ask you, and I include myself in this category, can anybody tell me if that number is divisible by 3 or not? The only sensible answer is no, I cannot tell you if that number is divisible by 3 or not. If you really force me to do this, I would convert this to decimal and then use some, people learn when you're a kid, you learn some tricks to tell if a decimal number is divisible by 3. So I would do that. But to me, I'm not able to just look at a binary number and tell you if it's divisible by 3 or not. I would convert to base 10, and then I'd be able to tell you. But actually, this can be done with a DFA. So this is my example of a DFA which actually can do an interesting computation, which is kind of hard for human beings to do. You might say this is only hard for me to do, kind of for cultural reasons, because I'm used to using base 10 numbers. If I somehow, since I was a kid, was only taught ever to use binary numbers, maybe as a kid I would have learned some kind of cute tricks for telling if a binary number is divisible by 3 or not. I don't know. People think in binary, I wouldn't think about divisible by 3. It'd be divisible by 1, 1. That's too weird for me to do in my head, though, because I'm not used to working with binary numbers. Anyway, we can make a DFA for this. Actually, the DFA is very simple. We don't really have time to get through it today, but a DFA can do this with only 3 states. Can you believe it? A DFA can make this computation using a DFA with only 3 states. And the three states have to do with, we'll do the details of this next time, but our three states that I'm going to think of are basically, this is, after all, something about numbers which are divisible by 3 or not, right? Now, when it comes to being divisible by 3 or not, there are actually kind of three options when it comes to dividing a number by 3. One is that it really is divisible by 3. One is when you divide by 3, you get a remainder of 1. There's like 1 left over. Or it could be that there's 2 left over when you divide by 3. All right? Those are the three possibilities. And so I'm going to write, my three states are going to be like this. Hopefully this is language you've seen before. X equals 0 mod 3. Or x equal 1 mod 3. This mod business means what's the remainder when you divide by 3. Or another way of thinking about it is it actually divisible by 3, or is it like 1 more than a multiple of 3? Or is it 2 more than a multiple of 3? Those are the only options. Or x equals 2 mod 3, right? And this is the starting state, because before you read any of the digits, the bits, you basically have an empty number which you interpret as 0, which is divisible by 3. And this is also the accepting state, because the intention of my machine is that it accepts numbers which are divisible by 3. All right. The big question is, where do the arrows go, right? And that, I think I'm going to leave that to next time. This is all complicated by the fact that, this is another weird fact, the DFA reads from left to right, which is kind of backwards in the traditional way that ordinary people read numbers. Like based on my upbringing, if you ask me if a number is divisible by something or other, I'm going to start by looking on the right side, because that's usually where the action is happening in terms of divisibility properties. But actually, this DFA reads left to right. This is somewhat weird in my opinion. But anyway, it is possible. Maybe I'll just leave it at that. Tantalizing thing. You can think about it over the weekend if you like. How do you put the arrows in here? That's what we'll do that at the beginning next time.